Hi, this is a video for compiler design, COMP442 and 6421. This is for week 9. So this week, we're going to continue our discussion on bottom-up parsing. In the previous video, I have presented how to do SLR parsing or simple LR parsing, presenting how to design the parser using the notion of item sets, and then constructing the table from the item sets. For this week, we're going to present further algorithms, LR parsing algorithms or techniques. So namely, I'm going to present canonical LR or LR1, and then present a little bit about LALR. Then we're going to talk about error recovery in the LR parsing methods. And then we're going to conclude by concluding remarks about parsing in general. Okay. So in the previous video or last week, I've presented an example using SLR parsing. I, of course, deliberately chose my example so that it does not have any problems. Of course, that doesn't mean that SLR parsing works for every grammar. So there are some cases, well, in most cases when the LR parsing or LR parsing method fails is that you would have conflicts. So this either is shift reduce conflicts or reduce conflicts. So if you remember when you design the table, design the DFA that corresponds to the grammar. So you try to achieve make a decision as to whether you will do a shift operation, which is going further above a terminal symbol, continuing the parse, or if you want to apply a reduce operation, in which case what you want to do is to remove a right-hand side from the stack and then replace it by its left-hand side. So there can be cases where you will not be able to make a decision, or there's going to be an ambiguity or non-determinism in the DFA, the resulting DFA. If, for example, if you have shift reduce conflict, here's an example. Let me bring in the pointer. So here you have, this is a very classical example. So what if you have your definition of if then else is either if E then S, or if E then S else S. So meaning that you want to have an if statement that has or does not have an else part. Now, this is creating the problem where, because of course this S here, because it can be another S, in which case you may have another if statement here. So in which case, if you have another if statement here, then if this other if statement starts here, and then you have else at the end of this other if statement, then you're not going to know if it's the else of the second if or else of the first if, and so on and so forth for any imbrication number of imbrications that you may have. So that's a very classic shift reduce conflict. So you see that this is the general case where in an LR parser, if you have a right-hand side that is a subset of another right-hand side for the same rule, for the same non-terminal symbol, then you will have a shift reduce conflict, which is that's just one of the examples. One of the cases where this may happen, but this is a classic example. So this is for a shift reduce conflict. So if you have this grammar here and you try to build an SLR parser, it is going, when you're going to want to introduce the items, the actions, the shift and reduce actions in the table, you're going to have a, you're going to want the heuristics that you use to put the entries in the table are going to tell you to actually enter more than one entry in the same cell of your table. One's going to be a shift action, the other is going to be a reduce action. So that's a shift reduce action. So you may also have reduce conflict. So I'll take this example of this grammar here. Again, another classic example, in which case here, if you design the DFA using item sets and so on, you're going to find that in one of the states, you're going to have these two items inside of the item set of this state. Now, if you recall, and what's happening here is that you want, when you have a finished item, then what you want to do using SLR is you want to use the follow set of the left-hand side in order to determine which entries of in which columns of the table you want to enter a reduce action using this rule. Now, if we compute the follow set of all the non-terminal symbols in this grammar, then we see that follow of S is $ and follow of E is $ plus equal. Now, if I want to introduce the reduce actions that corresponds to this in the table for this DFA, then I'm going to want at this state, at level of state number 3, under column $, I'm going to want to introduce reduce this rule or reduce this rule. So anytime you want to introduce a shift or reduce action in the same cell, in this case to reduce action, then that's a conflict. So in this case, reduce conflict. Now these happen quite often. It's not as, you know, let's face it, when we had to change, for example, our grammar in order to do top-down parsing, we were faced with many conflicts that we had to resolve by transforming the grammar. Okay. If you are using an LR method, there's going to be way less number of conflicts for a programming language grammar. There's going to be way less number of conflicts. I mean, in real life, you would have a much harder time designing a parser for a programming language grammar using top-down method than bottom-up method. But still, there is very often some conflicts like this. So that's why there is solutions for these problems. So for example, you may want to use canonical LR or LR1. Canonical LR and LR1 is a synonym. Okay, so what if, let's look at this grammar more closely. So the problem here happens because here in S, if I want to reduce here using this rule here, then this is basically that I was at this level here, and then I wanted to parse an S, and then S can be an ID, right? And then here, when I have eventually S can start with E, and then E can be E plus ID, or E gives ID. E can be an ID. This E here can be an ID also. So that's why I end up having these two items in the same item set. Okay. Because when you parse a Z, it starts with an S, and then if it starts with an S, it can start with an E, and then S and E can both be ID. So that's why I have these two items in this item set for this state. Now, the point is that when I use this rule here, if I would want to use this rule or this item here, so where was I before I actually ended up wanting to use this to process this ID here, to reduce this ID? Where was I before I actually started going on this particular right-hand side? But basically here I'm parsing an E. So where was I when I was parsing this E? I was actually here or here. So, and then, so that means that after this E, there would be equal and plus. So in this case, that's what I actually want to achieve here, that I'm gonna look ahead and see what is it that is coming after this E that I'm currently parsing here. Whereby here, if I'm parsing this S, what is after this S is actually the end of the program. So if I'm parsing this ID here, it's either I was parsing this S or I was parsing one of those E's. And if I went parsing an S, then the next thing would come is the $sign at the end of the program. Or if I'm parsing this E here, it's either equal or plus. Okay. So you see here that this is what the discriminant somehow that the SLR parser was using. It was using the follow set. Follow set is a much more generic kind of concept than this notion of look ahead, which is more precise to a particular application of or a particular derivation step. Okay. Whereas follow is general to all the possible derivation steps. So here you're using a much more specific kind of information. So look ahead set is these sets that are sets of terminal symbols that are actually used for doing the canonical LR parsers. So here, essentially, we're doing exactly the same procedure, except that we're keeping track of what is the look ahead set. So that, how does it work? So essentially what we do, you see that it's exactly the same format. I have my item sets for my states, and then I have my transitions from these to other states, and then I construct my new states, and then the closure, and so on and so forth, which creates other states and so on, and I proceed until I don't have any more states that have been to be created. Okay. Exactly the same procedure, except that here I'm adding this information here, which is the look ahead set for each of the different items. Now, what does that mean? Here I have this rule here, which is my starting item for this state 0. Of course, that's the starting symbol. Then what is it that, so that's my my first item set. So that item set, the look ahead, the look ahead set for my rule here is actually $. Why? Because what follows this S here would be $. So essentially the look ahead set is representing what is it that can actually follow this right-hand side here. Okay. So what is it that can follow this S? The end of the program. So if I'm parsing this S here and I parse this, then what is it that can follow this right-hand side is what can follow this right-hand side here. If you remember the notion of follow, you can see that this is, of course, related, but it's not the same thing as a follow set. Here it's only related to one particular path in the DFA. Okay. Whereas follow set is something very general that applies to any of the paths, in fact. Okay. So here, so the look ahead set of this here, this rule of this right-hand side here is $, because I started with this one here. Then if after I parse this S here, if this S is an E equal E, then what I have here should be what I had after the S, because this S here is the same as this one here. So the look ahead set for this item here is $. Now, if I take this dot here and I move it after the E, then I will get, so this E can be E plus ID. So what is the look ahead set of this here? So basically what is after where I was when I started this right-hand side? So where I was after before I started this right-hand side is here. So what is it that follows this right-hand side is what follows the E, which is equal. then I have my equal here as my look ahead set for this particular item. That's essentially saying after I parse e plus id here, what is it that will follow that, considering where I was when I actually started going my way forward in this right-hand side. So this E here can be ID. So after this ID, what is it can be? It's the equal here because that's where I started. So that's my look ahead set for this rule. Then I can actually be also parsing this E here. So if I parse this E here, what is that this E can be? Can be E plus ID again. But in this case, what follows this E is not equal, it's actually plus. So here I have added another new item that has actually the same item as this one, except that it has a different look ahead set. Okay. So you see that's what is different between the SLR, which I shown before, and this canonical LR or LR1. Here you have two items which are the same. If you'd be doing SLR, then these two items would be the same item. They would not be two different items. Here there's two different items because this E here is replacing this one here, which is followed by equal, and this one here is replacing this E here, which is followed by plus. So this is my new item, and that's a different item because it does not have the same item set, the same look ahead set. Then this E also can be an ID following this rule, and then what would follow this ID is plus. Then I could say, well, I'm going to still replace this E here, this E by E plus ID. Then that would actually be dot E plus ID followed by plus, which I already have. Okay. And the same thing with the E gives ID, replacing this one here, that would be E gives ID followed by plus, which I already have. So I already have all the items in my item set. Okay, so you see that it's a little bit different. The definition of the closure is different because you've added this notion of the item set. But overall, the concept is exactly the same, except that you consider what is it that's going to follow this right-hand side. Okay. So you see that the notion of the follow set is different from this notion of look ahead set. The follow set is a general concept that applies in all the possible cases of application of a non-terminal, whereas this here, the look ahead set, is what can follow a right-hand side only in this particular case in a previous sentential form that you were currently going forward into. So next thing you do is you have to somehow consolidate these here because you have some replications here. Like for example, here you have two items that are the same, and here you have two items that are the same. So these you must actually merge somehow into the same item by essentially taking these two items and then merging their look ahead set, thus forming from these two items here, forming this new consolidated item with the look ahead set being merged. And the same for this one here and this one here, which are merged into this one here. So I'm not going to, so here you know the concept, so I'm not going to repeat all the whole thing as I did in the previous video. So it's exactly the same concept that you repeat, exactly the same thing that, for example, if you are, I'm just going to remind you here, if you are, if this is your item set, keep in mind that what's happening. Let's go to the graph, which I have here. So this is my item set for state 0. So then what's going to happen is that I want to move the dot here. I want to proceed forward in these right-hand sides. So it's either I'm going to proceed forward with the S, in which case I'm going to go to another state where I have to transition with the non-terminal S. in which case I'm going to end up in state 1. Then if I move the dot after the E, then that leads me to state number 2. If I move the dot after the ID, then that leads me to state number 3. And I have 2 of these cases. So these 2 items are actually become the starting item set for this state number 3. And then the E, also the E case is this one here, where I take these 2 items that have an E after the dot, and after successfully parse an E, I come here with these items where the dot have been moved after the E, and so on and so forth. And for each of these, I would compute the closure of the item sets. Then I would come up with my completed item set, and then I repeat the process, determining the transitions, creating new states, and so on and so forth until I have computed all my closures and I did not create new states. I did not find transitions to new states that then need to be processed. So this is how it works. So you see that's very similar, except that it's using this very important concept here of the look-ahead set. It's not a radically different approach. It just uses crucial information that allows you to discriminate very accurately according to what is to be expected following a step into a particular right-hand side or path in your DFA. And that allows, essentially, that allows the canonical LR method to be a way more general method than the SLR method, because the SLR method is using the very generic notion of the follow set in order to apply a reduce action, whereas the CLR method or LR1 method is using this notion of look ahead set, which is much more fine-tuned to each possible cases and makes it better able to avoid many cases of conflicts in the grammar. Okay, so that's the final DFA for this particular grammar following the item sets that we found. Then the only difference, because now, of course, as we saw before, what you want to do is to be able to translate this DFA into a state transition table. Remind you for all the LR parsing methods, these methods rely on a table. They would basically translate this DFA into a table. All the tables are the same notion, that where you have an action table where you have your shift and reduce actions inside of the table, and a go-to table that is encoding to what state do you go after you have applied a reduce action, a specific reduce action. It uses essentially the same heuristics as what I've shown in the SLR method when I explained the SLR method, except that here, remember in the SLR method, what we had here, in order to determine where to put your reduce actions in the table, it was essentially using the follow set of the left-hand side of the rule in question. Here, instead of using the follow set of A, it would actually be using the look ahead set of the item itself. Okay, so you see this is where it's being more precise to each possible different case. Okay. Instead of using the general notion of the follow set, which leads to have more intersections, more conflicts. It's not to say that this method, by using this, is solving all the problems. So this is, for example, this is LR1. And here what's happening is that the item sets, the look ahead sets actually are, it's only the one next the one next terminal symbol that is coming in the parse in the program. So if it's possible that you have grammars for which you have ambiguities and the only first one is not enough, and then you may need to discriminate. You may need to have you may have two separate right-hand sides which are the same up to a certain point, and then the next token is not enough to make a discrimination because the difference between the two would come after the first one. So then what you would need to do is to have LR2, which would take into consideration the two next tokens. Okay, that's how you would have LR2, LR3, LR4, and so on and so forth. Okay. So the method would be the same, except that you would have to take into consideration what are not only the one next token, but the n next token, LRN. So eventually, if you apply these heuristics here on the item sets that we've computed before, as we have here, then eventually you would come up with a table like this from this grammar here. So essentially, this whole procedure is transforming this grammar here into a DFA using item sets and as well as the lookahead sets. And then you have these heuristics that you use that will go over all the item sets and will actually create this table. Then after you have the table, then it would use exactly the same algorithm as we have shown in the previous video using the SLR method. So whatever is the LR method that you are using, it is still using exactly the same algorithm after you have the table. The only difference is how do you generate the table. Now that was it. That's it for a very brief overview of what is LR1 or canonical LR. Thing with LR1 is that it creates a lot of states. For example, for a language, programming a typical programming language, you would end up having hundreds of states. Okay? So that's quite large, creating quite large tables. And even nowadays, this is problematic. So yes, our computers have a lot of memory, but when you have a large language, this is starting to become a problem. So if you want to optimize a compiler, you have to find a way to reduce somehow the size of the table. Of course, in the 1960s, when these things were invented, this was a crucial problem because the memory of computer, the amount of memory in a computer was much, much, much smaller than what we have now. So the problem is that CLR or LR1 generates more states than SLR. So SLR tends to necessitates lesser number of states. Of course, then SLR it's somehow handicapped by the fact that there's many grammars that it cannot deal with because, as we just saw, it suffers from being more prone to ambiguities or reduce conflicts. So for example, for a typical programming language, SLR table has hundreds of states, whereas a CLR table, the corresponding CLR table, will have thousands of states. So it's a very considerable difference between the two. Solution is to merge similar states. So basically what you're doing when you do LALR is that you find your CLR DFA, and then you look at your item sets for each of the states, and you will eventually find, for a grammar of a certain size, you will find states that have the same item sets, but maybe not the same lookahead sets for every item. So you're looking at states that have the same item sets, and then you will eventually merge them together, and then merge the lookahead sets of the items that were the same. So this is a rather, how can I say, a posteriori kind of description of what it is. So this was actually invented in the 1960s by Frank de Rimmer, the LALR and the SLR. You have to understand that when this was invented, the only thing that you had is that kind of generic LR method that was around. So then Frank de Rimmer from this actually invented this new notion. But it's easy to describe. That's basically nowadays. Basically, what I'm saying is that this is LR1 where you merge states. Where the fact of the matter is that when Frank de Rimmer invented LALR, the CLR was not as actually understood as we understood it. We understand it now. So after the fact, it's easy to explain it like this, but it's not how actually Frank de Rimmer invented it. So what do we have? So this is the same item sets that we had in the previous CLR example. So if we look at state 5 and 9, state 5 is here and state 9 is here. So if you look at state 5, E gives E plus dot ID. State 9, E gives E plus dot ID. So it's extremely similar, except that the look ahead set for these two is, for this one is equal plus, and for this one is plus $sign. So what I'm going to do is I'm going to say, okay, I'm going to merge these two and actually come up with a single merge state that is going to be E gives E plus dot ID, and then merge the look ahead set. I'm going to have equal plus $sign. Then, of course, I'm going to rearrange my transitions from there to state 8 as well as state 10, depending on the situation. So here is my state 5 and 9, and then I'm going to eventually come up with state 5, which is a consolidation of this state 5 and 9 here. And then here I can also see that state 8 and 10 have similar case, E plus ID dot, except that there is two different look ahead sets. So I'm going to merge these two as my state 8 here, where these two look ahead sets have been merged. Okay. So again, looks simplistic. Of course, this is not this is a kind of a posteriori, simple description of what LALR is doing after we have understood with many years what is the relationship between LR1 and LALR. And then eventually you would come up with a table like this. Now you might say, well, this is only a merge two states. This does not seem to be much because initially we had 10 and now we have 8. However, the larger is the grammar, the more number of rules you have and the longer are your right-hand sides, the more it's exponentially exploding the number of states that you will have. And it's also making it so in the process that you will have a much higher occurrence of states that have the same item sets and will then be merged. Okay. So the more you have number of states, the more you're going to have states that are going to be the target of merging, of being merged together. Now, this is, next thing is about error recovery. So we saw how you do error recovery in top-down parsing, especially for the, here, basically here we're using a stack, okay? So we saw when we explained how top-down parsing, top-down table-driven parsing is working, we saw that, well, it's using a stack. So what it wants to do is to either consume tokens and or pop things from the stack. Okay. So it wants, when it pops things from the stack, it basically wants to somehow forget that it was parsing a certain non-terminal. Okay. So here, this is going to be doing kind of the same concept, because of course it's using a stack. It's still a parsing algorithm. So there's going to be a lot of intersections between the concepts between this here and the LL1 top-down parsing, table-driven. So first of all, how do you detect an error? So if you remember when we were doing the top-down table-driven parsing, an error was detected when you would peek in the table and you would peek into an empty cell. Okay. Same concept is going to happen here when you peek into the action table using the algorithm. When you peek into the action table, if you peek in an empty cell, that's a parsing error. However, because you can also peek into the go-to table. If you peek into the go-to table and you come up on an empty cell, it's essentially impossible, which means that your table is actually wrong. Okay. Due to the nature of the go-to table, it just cannot be that you're going to peek into an empty cell. So what is it that that this is doing? It's doing this thing here. So first of all, if you find an error being that you're trying to peek into the action table, you found out an empty cell. So essentially going to pop the stack until you have a state S on top of the stack. You know, keep in mind that on the stack for LR parsing, there's alternating state symbol, state symbol, state symbol. So at this point, you had a yes, a state on top of the stack, and then you had a token and input. You peeked into the table, found an empty cell. So this combination of state and next token was invalid. So what you're going to do is you're going to backtrack to the next previous state that you had pushed on the table, on the stack. Then you're going to try to resume from there. Now, there are some cases where if you go back to the previous state that you had, it's possible that you still will not be able to continue from there. So basically, there are some conditions which are set up here, which I'm going to give an example later, or two examples later. There are some conditions for the parse to be resumable from the previous state you were in on the stack. Okay. And these are the conditions. So these conditions are essentially determined by looking up the various places in the table and figuring out whether or not it's possible to resume the parse from this particular state that was before in the stack. So you see that you determine what is the state S, which is this state S is the next state below in your stack. So you peek into your go-to table at this state S, and then this state S, first of all, must have entries in the go-to table. What that means, if the state S has entries in the go-to table, that actually it means that being in this state actually can be that you have just applied a reduce operation. Okay, so that's what you want to achieve with this error recovery. You essentially want to simulate that whatever you were currently parsing, whatever is the right-hand side you were on your way through recognizing as a handle, and you came up to a point and then it didn't work anymore. So what you want to do is to somehow forget that you were ever tried to parse this right-hand side. So you're going to want to backtrack until you were at the beginning of this right-hand side, basically that you come onto a state where you have entries in the go-to table, which would be a state where a state that you were before you actually applied a reduce action. So you were in a certain state before you went to this parsing this right-hand side. So you were in a state. Now you started being on your way in another right-hand side. So you came upon a problem here. So you want to somehow eliminate everything eliminate all the trace of you having been your way in this right-hand side and come to the point where you were before you started your way on this right-hand side. That's what that means. And that would be one of those states S that are a state that you are after you apply the reduce action. So essentially what this line means, you want to be in a state that is after the application of a reduce operation, whichever one it is. And then also that this S is the set of states in the go-to table for S. So in this state S, there are different entries in the go-to table. This is your state S, which is a set of states. And then T is the set of terminals for which the elements of S have a shift or accept entry in the action table. So whichever number of states that you have in this in the go-to table in this S state, what you want to do is that you want to be in a position where after you kind of simulated that you have applied this reduce action, you want to find yourself in a position where the next token is a valid token after you hypothetically have applied this reduce action. Okay. Essentially, that's what this third line here means. Okay. So you see that you're trying to simulate that whatever is this right-hand side you were on your way, the last one on top of the stack, you want to eliminate it. And then you want to set yourself in a position where some of the next token that you have is one of the tokens that is acceptable after you have applied a reduce action. Okay. And then once you have found such a case, then you actually skip tokens until you find a token that is in this set here. Okay. So you simulate that you have applied a reduce action by removing a right-hand side from top of the stack, and then you skip tokens until you have a token that is acceptable after this operation would have been applied. This reduce operation would have been applied. Then you actually push onto the stack this this non-terminal N here that you now have simulated that you have applied a reduce action for, and then you push its state in the go-to table, the state in the go-to table that corresponds to this non-terminal N that you are simulating that you've just parsed. Well, that's essentially repeating here into words, written words, what I've just explained. Okay. So here's an example. Very typical example is in a programming language, you have statements, and then the statements are typically separated by a semicolon. So every statement has a marker, which is semicolon. So whatever is the statement is, every statement has semicolon. So typically, if there is an error in a statement, then what you would do is to forget that you were parsing a statement, and then you would skip until you see the semicolon. Okay. So that's essentially one of the examples that this procedure would be doing. So that's the table that we had done for this grammar here. Okay, essentially, this is the SLR table for this grammar here that we designed in the previous video or last week. Here, what I've added is in the table, the errors. Okay, so anywhere there was an empty cell, I put error 1, error 3, error 1, 2, 3, 4, 5, 6, I believe. Yes. So these ones here. Okay. There may also be some of the errors which are actually a parser error, which are essentially impossible to peek into. Okay, so let's go with this here. So we have the stack here, the input here. You see that there is a problem here that this, well, this open parenthesis here is mismatched. And then there's also another problem here that you don't have an operation here. Okay. So eventually, as you may think, so you're gonna here be mismatched parenthesis, and then you're gonna skip this, and then you're gonna skip this, and then you're gonna somehow go ID times ID, and then you're gonna, of course, here find that this is a mismatched parenthesis. Essentially, this whole thing is going to finish, but having parsed successfully ID times ID, and then skipped this open parenthesis, this ID in the first place, in the first error, and then skip this close parenthesis in the second error, which I have highlighted in red here. So let's do this parse. So if you go 0 ID in the table, 0 ID is shift 5. So if you remember, when you have a shift action, you actually take this token here, push it on the stack, and then put the state number 5, which is shift 5, into your stack, onto your stack. And you go 5, close parenthesis. This is where it's going to start going wrong. So 5, close parenthesis, reduce 6. So here I'm actually reducing this. No, here it's going to start going wrong. So ID, so essentially here I'm having this ID on top of my stack. So I can actually say that this ID can be reduced into an F. So I'm going to remove this ID from the stack along with its state here. So I'm going to pop the 5, pop the ID, and then push the F, which is the left-hand side of this rule here. So reduce gives F ID, I remove the ID, replace it with F. And then I go into the table, 0F, and I see 0F is 3. So 3. And I go to the table again, close parenthesis, 3, close parenthesis, 3, close parenthesis, reduce 4. So this is essentially reducing this F here into a T. So I'm taking the F out of the stack along with its state, and then I push T here, and then I go to table 0T, and I will find 2. Then I go 2, close parenthesis, 2, close parenthesis is error number 2. 2, close parenthesis. Sorry. No, sorry, 2, close parenthesis, not open parenthesis. You see why a computer is better than me to actually do that. So 2, close parenthesis is reduced using this rule here. So I transform my T, I reduce my T into an E. So reduce the T into an E, and then in my go-to table, 0E, I find 1. Now this is where it's going to go wrong, E, close parenthesis. 1, sorry, 1, close parenthesis. 1, close parenthesis, error number 3. Now you see here I have actually created somehow error messages and I put them into the table. That's one of the things that is nice when you have a table-driven parser. You can somehow identify for each of the different cells, somehow give a general case of what is the error that is actually happening. So in this case, it's a mismatch parenthesis. Now, this is how we will enter this whole thing here of the error recovery. So here we pop until we find a state S on top of the stack that is, and T is not empty. So we pop until we find a state S on top of the stack. So we pop until, well, we pop, of course, the 1 because we know it's wrong, and pop E because it's not a state, and we come on to 0. Now, in 0, we see that in state 0, under the go-to table, we have, for ETF, we have 1, 2, 3. This is where we're going to start using what I have on the board here. So for state 0, what I do is I eventually going to want to compute the T set. Now, first, for the T set depends on the S set. What is the S set? S is the set of states for which this state number 0 here, for which I have an entry in the go-to table. So the set big S is actually the state, the set of states 1, 2, 3. So if I go under the in the go-to table in state S, I find state number 1, 2, 3, and they correspond respectively to non-terminal E, T, F. So I have a mapping between E and 1, T and 2, and F and 3. Okay. Then eventually I'm computing my set T. Let's go to the definition here. I remind you, this was my S. This is the state I pop until I find a state S. Then the big S is the set of states that you find in the go-to table for state S. So in this case, state 0 has entries in the go-to table. If it would not, then I would continue popping until I find the next state that would have entries in the go-to table. Okay. Of course, my two cases are rather simple. Then I compute the T. Now, what is the concept of the T? The T set is actually for every of the states that I have found in the S set, I compute T of this state. What is this set? T of 1. T of 1 is actually the, if I go into state 1, and I scan over all the elements in the on all the columns for this state. I scan and I try to find some accept or shift actions. So if I go into the table, for state number 1, and I'm looking for shift or accept actions, I see plus and $, shift 6 plus accept $. So plus $, is the T set of state number 1. Okay. So that's what it's going to tell me if I'm actually want to pop until I find one of these here, then I would have to actually simulate that I have applied a reduced action leading me to this one here, in which case I'm going to use this this pair here. Whereas if I'm using this one here, then I'm going to actually be using this pair here, because here this is T of 2, which is identifying with having already parsed a T in the go-to table. So, and then this is for T of 1. So what about T of 2? T of 2 is here. This is a reduce. That's not good. Okay, yes, sorry. And then I have my shift action here, state number 2, shift action times. So, and then there's none other than this. So that's only T of 2 is times. Then if you go to state number 3 and you try to find a shift or accept action, you see that there is none. So the state T of 3 is the empty set. Okay. So eventually what I'm going to want to do is synchronize using, it's essentially some kind of synchronization set here that I found. Okay. I want to simulate that I have applied a reduce action and that my next token is going to be one of these. After the simulated reduce action. So essentially what's happening here is I'm removing the 1, removing the E, and then I come to 0. And then eventually what I'm going to do is that I'm going to find out that for star here, that I want to actually find myself using the star here. I want to find myself in the state number 2, which is having been successfully parsed a T. Because what I want to do is, of course, skip tokens until I find this token here, times. So I remove the 1 and the 0. I find myself is 0. Then I compute this here. And then I find that I can resynchronize using the star here. So I eventually pop until I find the star. And then I put the star corresponds to state number 2, which corresponds to non-terminal T. So I push T and 2, and then I pop until I find the star. Then I can reduce, I can resume the parse. And of course, it's going to be very magical that it's going to work because I just made it so that it's going to work. Of course, I go to state number 2 and star, and then I find quite magically that this is shift 7, which I just identified when I determined where I would synchronize to. Then, so shift 7, I push the star here and I push 7, and then 7 ID, shift 5. So I push the ID here, push 5, and then 5 close parenthesis. This is telling me to apply reduce F gives ID. I remove the ID and its accompanying state here, and I push the F. Then I go 7F in my go-to table. I find state number 10, push it here. 10 close parenthesis says reduce using this rule here, T times F. So I pop 1, 2, 3, I pop 6 things from the stack. 1, 2, 3, 4, 5, 6. I have 0 on top of the stack. And I push T on top of the stack, which is the left-hand side here. Then I go in my go-to table, 0T, I find state number 2. Then 2 close parenthesis tells me reduce using E gives T. So I pop the 2 and the T from the stack, and then I'm left with 0, and then I push E onto the stack. Then I go in my go-to table, 0E, I find 1, and I push the 1. Then again, you see, I'm in the same situation here. Then I'm actually applying this error recovery procedure that I've done before. Luckily, in this second example, I still have state 0. When I pop this 1 and this E, and then I'm come up to 0, it's the same analysis here. Okay, except that in this case, I will pop. I will consume tokens until I find one of these here, and then eventually I'm going to consume this one, throw it away, and then come with this one and then see that it's here. So because this one is here, this corresponds to state 1, which corresponds to this entry in the go-to table. This entry here, which corresponds to E. So basically here, I'm going to simulate that I've successfully parsed an E. and that I have applied a reduce operation that has E as a left-hand side. So that's why I'm going to push the E, because that's the E I have here. And then I'm going to go to table, of course, 0 E, I will find 1. So that's what I push here on my stack after I resume the parse. And then, of course, I'm going to come into the table, $1. What you think I'm going to find is accept. Okay. So here I have successfully twice recovered from an error. So I remind you that what's the overall result here that was achieved is that I successfully parsed this ID and then skipped these two, and then successfully parsed the times, successfully parsed the ID, skipped the close parenthesis, and then successfully parsed the end of a string. So this is how you do error recovery and LR parsing. And because all the LR parsing methods are using the same go-to and action table, they're all using the same error recovery technique. No matter if you're using items, lookahead sets or not, they're all using the same recovery method, which is the goal is to somehow you were going your way in a certain right-hand side. You want to somehow forget that you were going your way on this right-hand side and resynchronize as though you would have successfully parsed this right-hand side, and resynchronize your your parsing stack according to the fact that you would have successfully parsed this right-hand side, and then consume tokens until you find something that follows this right-hand side, which is something you find in your actual table. So that's it about the description of the LR methods, or the bottom-up methods. There are some other methods. Again, here I'm not claiming to be complete. There are some other parsing methods which I'm not covering here. Some bottom-up methods which I'm not covering here. So another thing, of course, in real life that you would be doing is using a parser generator. So of course, we saw that constructing the table is extremely laborious and error-prone. So, but it is something that is done through a process. So what you want to do is to automate this process of creating the items and then creating the tables. Okay, and then of course you can use a generic algorithm that will peek into the table and parse the language that was used to generate the table. So you would have, for typical programming language, you will have thousands of states. Okay, so that's not something you want to do manually, of course not. So that's why you have parser generators that have been designed that will automatically generate the table. Depending on what parsing method that they are using, the table would be of a different size. For example, if you're using SLR, table is going to be somehow smaller, but it's not going to be able to accommodate as many grammars as, for example, an LR1 parser, which would be able to accommodate a much larger number of grammars, but would also generate much, much larger tables. Then if you want to come with a compromise, then you can use the LALR method, which is doing merging of states and so on, as I explained before. And that's, in fact, what many of the parser generators are using, the LALR method. So many of these tools are offsprings of YAC. YAC is a tool that was invented again in the end of the 1960s, beginning of the 70s. And that's one of the first such tools that was invented that was using the LR method. This tool and many of its variants that are now existing nowadays and are still used nowadays, they are using the LALR1 method. So how does these tools work? So essentially you give the grammar to the tool in a specific format, which is kind of a BNF format. Then the tool will detect an attempt to resolve some of the conflicts. If it can, often it cannot, and then you would have to manually fix the grammar. So it requires really a minimal number of changes to a grammar. Here, again, we're talking about programming language grammar. You can find a lot of grammars that are actually not parsable using LALR. But if you're talking about programming language grammars, then you've reduced the number. You don't have that many programming language grammars that would be impossible to parse using LALR method. And then eventually you have to consider the notion of introducing the semantic actions. So you can, in using these tools, as you provide your grammar, you actually insert the semantic actions, which are generally at the end of every of your right-hand side in sides in your grammar. So you can insert semantic actions in the input you give to the LALR parser generator, and it would eventually create a parser that will call your semantic actions. For example, generating the AST. Then typically the AST would be used by a backend that will eventually do the semantic analysis and the code generation. You could have the parser generator to inject the semantic checking actions and the code generation actions, but that's that's much easier, let's put it this way, to generate an AST from the parser and then traverse the AST to do the further processing stages. That's how it's done in vast majority of cases of in real life. So what is it that you should use? First of all, top-down parsing. So you have make a choice according to what I've covered. So either you have top-down parsing, recursive descent predictive parsing, table-driven predictive parsing. For the bottom-up methods, we saw SLR, CLR, and LALR, or a parser generator. So what are the advantages and drawbacks of these? Well, as we saw for real-life cases, if you do recursive descent, which you code yourself, problem is that it's not very maintainable. If you need to change the grammar after the code has been written, you have to scrap some code and then rewrite it according to the changes in the grammar. It's not very maintainable if it is hard-coded. If you coded it yourself. There are actually some parser generators that will generate a recursive descent predictive parser. That's generally speaking, this is done for kind of academic purposes for the sake of showing that it's actually possible. Of course, when you do, as we saw in the project, the necessity of having to change the grammar is making things much more complicated when you want to use a top-down parser. So even if you would have a parser generator that would be a top-down parser generator, you would still have to change your grammar and remove the ambiguities in your grammar before you would use the parser generator. Code generation and error detection is more difficult and less accurate in top-down parser. So there is some cases where a top-down parser will actually detect or figure out that there was an error after the actual occurrence of the error itself, which makes it so that it's not going to be very accurately report the error to the programmer. So that's one of the disadvantages of the top-down parsing. In real life, most of the compilers implemented a variation of the LR methods using a parser generator. There are many parser generators available. I've used Antler, for example, the tool that I have designed to do the removal of the left ambiguities and so on and so forth. I was actually using Antler to design it. You also have Yak, and it's one of its offsprings, Bison. You have others like a Java CC or a Sable CC. You have plenty of such tools that are available. Okay, so in real life, you would use, yes, a parser generator. There is also even more powerful methods than the SLR, the CLR method that I've shown. One of them is called GLR. So what GLR is doing is that, you know, when you have an ambiguity or shift reduce conflict in an LR parsing table, is that it doesn't, basically the parsing method does not know at some point in time whether it should apply shift or reduce. Now, a method like GLR, what it does is that it's going to try both. And then it's going to see what happens in each of the two cases. Of course, as it goes into each of the two cases, and it's likely that it's going to also have to branch out in every of these branches. So basically what it's doing is that it's constructing some kind of tree of derivations. It's going to try the possible avenues for every ambiguous case that it came upon in the parse. And it's going to branch, and eventually it's going to find out that there's going to be one of those branches that successfully parses the program. Thus, it would have successfully parsed the program, successfully build one derivation, one of the possible derivations along these branches that actually successfully parses the program. Of course, this is kind of wasteful of resources because it is actually computing many branches, and only one is going to result in the successful parse. Okay. Nevertheless, that makes it very interesting because sorry, you don't have to resolve the ambiguities as you give the grammar to the tool. So there are, yes, some new things that are invented. Well, this is rather new. This was came into being, I believe, in the late 80s. Of course, you as a 20-something-year-old would say, well, this is a long time ago, but it is kind of later compared to the LR methods and so on, which are invented in the 60s. So yes, there are still some things that are happening in compiler design, but not that many things, and they're always kind of a variation of things that were invented in the 60s and early 70s. So that's it for this lecture. Thank you. Bye-bye.